Okay, in this video I wanted to finish up section 12.2. We're talking about logarithms, and we've already gone over the definition of a logarithm. We've used that now several times in these problems. Y equal log base a of x means that x equals a to the y. In the last video I had shown you the graph of y equal log base 2 of x. We were getting that from the graph of y equal 2 to the x. Remember that y equal log base a of x and y equal a to the x, those are inverses of each other. Then we looked at the natural logarithm. Okay, that was problem 11. Y equal the ln of x and y equal e to the x are inverses of each other. Okay, and that's really the big reason for caring about logarithms, is that a logarithm is the inverse of a corresponding exponential. We're on problem 12 now, okay, and we've introduced the natural logarithm here. Let's do some calculations with the natural logarithm. Okay, natural logarithm again just means that you're working with base e. So let's find the value of, like in part A, we want to find the value of the ln of e. Well, if I call that y, I need to know the value of y, and then I'm done, right? The actual number for y. Well, I can use the definition and rewrite this into exponential form. Okay. Right now I'm in the logarithmic form, so let's rewrite that. E is the input. Okay, so that'd be my x value. That's going to go all alone on the exponential. The ln notation means that you're working with base e. Okay, so this e here is the base of the logarithm. It's not going to be the base of the exponential. Y would be the power of e. Okay, so I'm looking at e to the y equal e, which is now this equation but rewritten into an exponential form. Now, the only possible value for y to have this be a true statement would be 1. E to the first is e, right? If y is any other value, you wouldn't have a true statement there, okay? Y is 1. So the ln of e, that's 1. Part B, the ln of e squared. Well, let me call that y and then use the definition. E squared is my input, so that's going to go all along the exponential. The base is e. Y would be the power of e. Okay, e to the y equal e squared, that means that y is 2. So the ln of e squared is 2. Actually, the ln of e to a power will always be that power. So the ln of e squared is 2. The ln of e to the 6th is 6. The ln of e to the negative 4th is negative 4. The ln of e to the 1st is 1. Okay, the ln of e to a power is just going to be that power. Well, part C, the ln of 1, well, if we call that y, x is 1, e is the base, y would be the power of e, 1 equal e to the y would be the equation now in exponential form. And, okay, anything the 0 power is 1, right? E to the 0 would be 1. So if you have e to the 0 equal e to the y, remove the base and set the powers equal, that means that y is 0. The ln of 1 is 0. Now I had mentioned earlier that log base anything of 1 is always 0. We looked at that in problem 9c here. Log base anything of 1 is always 0. So it doesn't matter, if it's base 5 or base 3 or base e, doesn't matter. Okay, log base anything of 1 is always 0. Now these calculations involved no calculator. Part D actually will involve a calculator, okay, because you see, if I were to let y be equal to the ln of 2 and then apply the definition, I would have the equation 2 equals e to the y. Now 2 cannot be rewritten as e to a power, and at least at this point we can't easily do that. So there's not going to be a way to get the same base on both sides like I was able to do over here. Now, most calculators have an ln button on it. Okay, so like this model is is here's the ln button. Okay, and I can type in the ln of 2, and that's roughly 0.693 if you go nearest 3 digits. Okay, on this model, okay, here's the ln button. The ln of 2 is same thing, 0.693 if you go nearest 3 digits on that. Okay, now the fact that it has an ln button means that I could have done, you know, all these 3 problems, but using the calculator. You know, I could have checked that the ln of e is 1. Okay, it's just I didn't need a calculator to do that. Okay, most calculators have a log button and an ln button. Okay, but they can't do other bases. Some can, okay, but a lot of them don't have that option set up there for you. All right, now there's some problems in this section where they want you to solve some logarithmic equations. This is kind of an introduction to that. Later in the chapter, you do some more with equations, and you know, because there is more to know here. But let's take a look at problem 13. We're going to solve for x. Okay, now a lot of the logarithmic equations are going to involve using the definition of a logarithm and then the properties of logarithms. We're going to talk about the properties of logarithms in the next section. Okay, so at the moment we're just going to use the definition on every single one of these actually. Well, y equal log base a of x means that x equal a to the y. So let me apply that here. X equals so the 5 is the base, 2 is the y value. Okay, and so I'm looking at x equal 5 squared. Well, the nice thing about using the definition here is that I no longer have the logarithmic notation. I like that because now I'm back on familiar ground, right? 5 squared is 25, so x equal 25, that'd be the answer. Part B, log base 2 of x equal negative 3. Now, same deal. I want to rewrite this into an exponential form. 2 is the base, negative 3 is the y value, so x equal 2 to the negative third, or x equal 1 over 2 cubed, x equal 1/8 would be my answer. Okay, here's another one. Part C, log of x equal 3. Now remember that if there's no base, it's understood to be base 10. You can write the base if you want or not, doesn't matter. Okay, but still know that you're working with base 10 there. So having said that, the base is 10. 3 is the y value, right? X equal 10 cubed would be the equation now rewritten into an exponential form. 10 cubed is 1,000, so x equal 1,000 is the answer. Part D, the ln of x equal 3. Well, so the natural logarithm means that you're working with base e. E is the base, 3 is the y value, x is the input, right? So x equal a to the y, and this problem means that x equals e to the third. Okay, so e cubed, if you were to go to the calculator and type that in, e cubed is roughly about 20.086 if you go nearest 3 digits on that. Okay. Part E, okay, solve for x. Well, again, I'd want to use the definition here. 4x minus 7, that's the input into the logarithm, so that's going to be all alone now on the exponential. 3 is the base, so it's now going to be the base of the exponential. 2 is the y value, so that's going to be the power of 3. Okay, and I no longer have the logarithmic notation there, which is what I like. Okay, 3 squared is 9. If you add 7 to both sides and then divide by 4, you get x equal 4 is the solution. Part F, log base x of 64 equal 2. Solve for x. Well, again, let's use the definition there and rewrite this into an exponential form. X is the base, 2 would be the y value, right? So x squared equals 64 is the input, so that's going to be all alone on the exponential. X squared equals 64. If you take the square root of both sides, don't forget about the plus or minus when you do that, and you'll have x equal plus or minus 8. Now, we were told that the base of a logarithm has to be a positive number. Oops, right here. Base is always a positive number. Okay, so in this problem, I would disregard the negative 8 that came up, and x would be 8. Okay. A logarithmic equation is a kind of equation where you can sometimes have extraneous solutions. There's more information about that later in the chapter, because I mentioned that there is more to know about solving logarithmic equations here. This is kind of an introduction to that. Let's take a look at part G. Okay, solve for x. The ln of x minus 5 equal 2. Well, let's rewrite that into an exponential form. The base is e. 2 is the y value. X minus 5 is the input. Okay, so that's going to be all alone on the exponential. Well, if you add 5 to both sides, e squared from earlier, when we had done that, e squared was roughly about 7.39 if you were to check that in the calculator. Okay, add 5 and you get roughly about 12.39 or 12.4 if you go nearest one digit. Okay, and here's another one. Okay, log base 4 of 64 equal x. Solve for x. Well, again, let's use the definition of a logarithm. Let's rewrite that into an exponential form. 4 is the base, x is the power of 4, 64 is my input, so that's going to be all alone on the exponential. 4 to the x equals 64. Okay, I am now in exponential form, so I'd want to get the same base there. I can do that. In this one, I can get base 4 on both sides. 4 times 4 times 4, 4 cubed, that'd be 64. So where I see the 64, I'll rewrite that with 4 cubed. Now I've got base 4 on both sides, so I can remove the 4's and set the powers equal. X equal 3 would be the answer on that one. Okay, and then at the end of the section, they got a couple of application problems mixed into this, so here's just one that I liked. Problem 14, wind speed typically varies in the first 20 meters above the ground. For a particular day, let the formula f of x equal 1.2 times the ln of x plus 2.3. Compute the wind speed in meters per second at a height x meters above the ground for when x is greater than or equal to 1. Okay, so think of that as like the domain of f. Part A, find the wind speed at a height of 5 meters. Okay, well, x is the wind speed. What did it say here? F of x is the wind speed, right? X is the height above the ground. So if I want to know the wind speed at a height of 5, I just plug in that number, 5, and I can go to the calculator here and type that in. Okay, so the ln of 5 times 1.2 plus 2.3, I'm getting roughly about 4.2 meters per second. Okay. So if I'm 5 meters above the ground on this particular day, the speed of the wind would be roughly about 4.2 meters per second. Part B, the graph of f of x is shown below. Interpret the graph. So if we were to graph this curve, here's the curve that we would get. Okay, it kind of increases here and then starts to flatten out. Okay, and by the way, I think that this curve would make sense on pretty much any normal day. Typically, the speed of the wind is going to vary more when you're closer to the ground. But then at some point it's going to level off. Okay, that's why planes fly real high in the sky. That's why birds fly high in the sky, right? Because the wind is not whipping all around way up there like it is closer to the ground. So a curve like this, makes sense for this particular problem. When we interpret the graph, we would say that at first the wind speed is increasing, okay, but then it starts to level off, okay. The higher that you are above the ground, it's not going to be as windy as it is when you're closer to the ground, in other words. All right, so that's all I had in this section. Hopefully that's enough for you. The homework here is on page 969. Be sure to look at the odd numbered problems for me.